All right, here we are finally with the last of this very long three-part lecture. So here we're going to finally wrap things up, and we're going to talk about how to actually sketch these functions that we've been so deeply interested in, and how to actually do a really accurate sketch of these. So let's go ahead. Basically, all we're going to be doing is just continuing with the example that we saw last time. So just refreshing ourselves on that, we had this curve, x times x plus 5 squared. And we had done a lot of work on this before. We had found f prime of x. We had found f double prime of x. We found, well, from that, we found increasing, decreasing. We found critical points. And then from the second derivative here, we found concave up, concave down. We found all these regions. And then we also found inflection points. And then also, not to forget, we also found for f of x, we found positive, negative regions of that, as well as x-intercepts or zeros or roots. And so all of that info we've actually got summarized in these number lines. And we made these number lines, I've cleaned them up a little bit. So what we have here is we have for f of x here, we have our x-intercepts at 0 and -5. For f prime, we have our critical points, -5 and -5/3. And for f double prime, we have a possible inflection point at -10/3. And we'll note that because the concavity changes sign from negative to positive at this instant, at this possible inflection point, this is actually an inflection point. So we can confirm that that is an inflection point. We also have for these regions here, all 8 of those, we have the actual values of f, f prime, and f double prime in the corresponding regions. So, looking something like that, and that, and so on for the other ones. And so that will tell us where our function is either positive or negative, where the derivative is positive or negative, which means where the original function is increasing or decreasing, and where the second derivative is positive or negative, which means where the original function is concave up or concave down. So we have all this right here. We summarized this in this nice, just one slide right here, all the regions where we're positive, negative, increasing, decreasing, concave up, concave down. We've written our zeros, we've written our critical points, we've written our inflection points. We are almost ready to graph this. There's just one more step that we actually have to do. So that step is basically saying, hey, we've got all these important points right here. What I want to do is I want to find the y values that correspond to each of those points. And so what we're going to do is we're going to just take all those points. So that was 0. We had that -5/3. We had -10/3, and we had -5. And I'm going to evaluate the function f at each of those points. Yeah, so when I evaluate f at each of those points, we'll go ahead and do that. And for some of these, I'm not going to bother doing all of them fully out. Like this one is simple. We just get 0 because there's a 0 multiplied there. This one is also simple because we end up with -5 times 0 squared, which is just 0. I'm going to skip the work for these middle two. And just note that we get -500 over 27, and here we get -250 over 27. So while those look weird, that's fine. They're just fractions. We can deal with those. And so what we have here is we have 0, 0. We have -5/3, -500 over 27. we have negative 10/3, negative 250 over 27, and then squeezing it right in the bottom there, negative 5 comma 0. And so this is great because now we have everything we need to know. We have all of our regions where we know the function is positive, negative, increasing, decreasing, concave up, concave down. And now we have the actual coordinate points for all of our zeros, all of our critical points, and all of our inflection points. So let's actually go ahead and let's actually sketch this thing. So you can see I've got my points right here that we just solved for. And I am going to label those points A, B, C, and D. And obviously in a case like this, it might be helpful to have like a calculator to know exactly what decimal that is or exactly where it falls. If I were giving you an example to do on like an exam or something like that, the numbers would work out a little bit nicer. But basically what we've got here is these are our 4 points. And I've graphed these electronically, if you will. So these are exactly right there. You could make these notes that right there is negative 250 over 27, and that right there is negative 500 over 27. That right there is negative 5. That right there is negative 10/3. And that right there is negative 5/3. So you could put all these labels and all these tick marks. I think that's very helpful to do that. For now, I'm going to leave those off just so that I'm not cluttered. At the end, I will actually label my points appropriately. So I'm going to go ahead and take away all that just so we don't have a cluttered graph. So this is what we've got here. And now, basically, I'm just going to keep flipping back and forth between the graph and the actual sort of those number lines that we saw from before. So let's start off. And what I want to do is I want to look at this region out here. So these X values. So basically, I'm just going to look at this part of the graph right there. I don't care about anything over here. I don't care about B, C, D. I don't care about any of that. I just want to know from negative infinity up to negative 5, which is that X coordinate for this point A right there. And so let's go back and let's look at our number lines here. And so what I notice is when I'm looking in that region from negative 5 and over, then I can actually just read off what my values of f prime and f double prime are. I see that f is negative in that region to the left of negative 5. I see that f prime is positive, and I see that f double prime is negative. And in fact, f double prime is negative as long as I'm to the left of negative 10/3. So that's good, but definitely it's going to definitely be negative to the left of negative 5 if it's negative for all of this over here. So really what I'm looking at here is I'm saying, all right, my function has to be negative. So right off the bat, I better graph my function down here. I better not have anything up here in this positive region. My function better only exist down here because we see right here that it's in fact negative. And then my function better be increasing and it better be concave down. And so what we can see here is if I'm negative, I'm increasing and I'm concave down, there's really only one possible thing that I can draw, and that's going to look like this. So you'll notice I am negative because I'm below the x-axis. My function is increasing as I read from left to right, as I read across the graph like that, reading from left to right. My function is going up. Don't let this arrow fool you. That arrow is just indicating that it's going to keep going down forever. I am increasing. My function is getting larger and larger as I move from left to right. And so, and then lastly, I'm concave down, right? If I had drawn something that looked like this, that that would be, while that would be negative, it would be below the axis, it would be increasing. It's not concave down, that's actually concave up. It's smiling, if you will, in the green there. But this red is concave down. And so really that's just it. That's all we have. That's the only option for what we can draw, because we know that it has to be negative. We know that it has to be increasing. We know that it has to be concave down. And we know it has to go through this point at -5. And let's actually hone in, now that I'm mentioning that, let's hone in on this point at -5. Well, we saw that we had a 0 at -5. We had an x-intercept, and we had a critical point. So two things have to happen at -5. It has to cross the x-axis, or at least touch it. And it does right there. And then also it has to be a critical point, which means the derivative has to be 0. What you could probably guess from here is that this is going to look like that, and it's going to go down, and it's going to come back up. I mean, you can see kind of just how this is going to connect the dots, and it's going to go. And we'll get to those regions in a second. But basically, I have to have a slope of 0 right there because it is a critical point. So keep that in mind. All right, so we have that right there. Now, let's continue on. Let's go ahead and look at the region in between A and B right here. So that is from -5 to -10/3. Right there, you can see those x values for A and B. So I'm looking in between -5 and -10/3. And if I do that, I'm going to be looking in this section of my number line. And so only look inside that red box and ask yourself, what's my function, what's my derivative, and what's my second derivative in terms of sign. And what I notice is that in this region, my function is negative. You can see that right here. My function is negative in between -5 and 0. For this whole region here, all of these x values, my function is negative. And so definitely in this region right here, excuse the not straight lines there, in that region, it's also negative, right? It's negative for all of this, so it's definitely going to be negative for this part. Same thing goes here. My derivative is negative, and then my second derivative is also negative right there, just in that region. And so there we go. So we know that actually all of these are negative. So let's keep that in the back of our minds when we're going to graph. So my function is negative, so I better not draw anything up here. I better only draw down here. It has to be decreasing, so I have to go down, and it has to be concave down still because my second derivative was negative. And that leads us just to one possibility of things that we can draw. Ooh, let's make that look a little better. Right, like that. I'm negative, so I'm below the axis. I am decreasing, I'm going down on the y with my y values, and I am concave down. I am still frowning. If I put my eyes up here, I'm still frowning right there. Let's go ahead and actually make this the same color there, make it look nice. So right there we go. We've got our section from A to B. We're negative, we're decreasing, and we're concave down after looking at that, looking at our number lines right there. All right, same deal. Let's look at the region from B to C right here. And so we're going to be looking in between -10/3 and -5/3. So let's go back to our number line. So we're going to be looking at this region, that region, and that region right there. And it should be pretty clear by now. I have a negative, and a positive. So I am negative for my function values, I am decreasing, and I am concave up. And so let's go back. I'm negative, meaning I definitely can't be up here. That's probably obvious because my function is already negative. I'm decreasing, so I keep going down, but I'm concave up, so I don't want to draw it like that. That would still be concave down. I want to draw it like that. And that's exactly what we'll do. Continue this down. And what do I notice here? Well, I notice a couple things already. I notice at A, like we said before, I have an intercept at A. That is an x-intercept there, and that's what we wanted. We had a x-intercept at -5. Also, we had a critical point at -5. So do I? Oh, look, there's a slope of 0. Good. And then what we also saw was that -10/3 was in fact an inflection point. And so the concavity has to change. And when I look right there, I notice that I move from frowning. Let's draw that a little better. I move from a frowning state to a smiling state. Maybe I can continue that up. And you can see that right at B, I change from frowning to smiling. And so that is a change in concavity. And so we've drawn this appropriately, point B being an inflection point. C right here, we've got that. We had before that this point C at -5/3 that in fact was a critical point. We'll confirm that once we keep on graphing. Let's look at this region from C to D, which is from -5/3 to 0. And we'll go back to our number lines. So from -5/3 to 0, I'm looking at those regions right there, and you can see that I am negative, I am positive, and I am positive. So I'm still negative on my Y values. I am increasing now, and I am concave up still. So we'll keep those in mind. I'm still negative, so I better not put anything up there. I better only draw down here. I'm increasing, so I better go up, and I am concave up. So I don't want to draw it like that. That would look bad because that's concave down. So our only option really is that. And there we go. We've got that right there. And so we do in fact notice that we have a critical point at point C, which is x equals -5/3. And we had that right there, critical point. So there we go. Last region is going to be from point D onward. So that's going to be from 0 and greater. Let's go back to our number lines. We'll notice on 0 and greater, I am positive, positive, positive right there. And so everything is just positive. We can go back to our graph and we can draw it appropriately. And if we do that, we're not going to draw anything down here because that would be negative. We want to draw up here because that's where we're positive. I am increasing, so I definitely have to go up, and I have to be concave down still, or excuse me, concave up because our second derivative is positive. So I don't want to draw it like that. That would be concave down. You can tell this is frowning right there. That's bad. That's a frown. So we don't want that. We want to actually draw this just going up and up and up and still in that smiling phase, if you will. So we are in fact smiling from B onward. That looks like a good old smile to me right there. Boom. And so right there, we've done it. We've graphed this. We have our points, and actually, I mentioned earlier that I was going to label my points. I've actually already done that. Really, I have labels A, B, C, and D, and I state right off here on the side what A, B, C, and D are. That's totally fine. I personally like doing that because I think it makes it a little bit less cluttered. You don't end up having to write, -5, 0, and then -10/3, and trying to squeeze it all into these small points. So just write my letters A, B, C, D, and I tell you what those are right off to the side. One last thing that I think is a bit important to notice is that we got a little lucky here, and we actually have the value of our y-intercept because the function went through the origin. In general, the y-intercept is a great point to find if you don't already find it in your work for finding x-intercepts, critical points, and inflection points. We got lucky here. One of our x-intercepts was also the y-intercept. But in general, that's a good idea to find the y-intercept. And all you do for that is you just set x equal to 0. That's just a simple algebraic maneuver. You set x equal to 0. You're just evaluating f of 0, and you're seeing what you get, and that's your y-intercept right there. So that's just another added point just for a little bit more specificity, just a little bit better of a graph that you can get. But here we already have it, so that's great. We've got our graph right there. This is pretty much it. That's really all we're doing. We've done the bulk of the work in that last lecture, with these number lines right here and these this just sort of summary of everything that we have right there. The only extra thing we did today was we found the y values that corresponded to all of these, and then we just graphed it. There's two other things that I want to mention before we go. I know sometimes it was a little weird looking at, like I was saying, hey, if we're just looking in between -5 and -10/3, trying to figure out where that, hey, is my derivative positive or negative? Well, just notice that this sign right here, this works for this entire region. So if I'm just looking right here, then this sign corresponds to anything in here. And same thing, if I'm just looking between -10/3 and -5/3, this plus is what it corresponds to, because this plus works for this entire region, right in there. So that's one thing I want to mention. The second thing I want to mention, and I've kind of done this on as we went through, but I want to point out sort of the possibilities of what I can draw based on the values of these signs and all the combinations that you can get. And so let's go ahead and take a look at this. I'm actually gonna make a little grid here. So let's say that I am increasing and concave up. Let's say here that I'm increasing and concave down. Let's say I'm decreasing and concave up. And let's say I am decreasing and concave down. So looking at just the first and the second derivative, these are all four of the combinations that you could have, right? You could have, plus, you could have plus, minus, you could have minus, plus, and you could have minus, minus for that first and second derivative respectively. And hopefully what you'll notice here is there's really only one way that you can draw these. Like that's increasing and concave up. This is going to be increasing and concave down. This is going to be decreasing and concave up. And this is going to be decreasing and concave down. And that's it right there. That's the four sort of curves that you can draw. Obviously, with each of these curves, you can draw them for positive y or for negative y. That's just saying if it's above or below the axis. But in terms of the shape of the graph, this is it. These are your four options. You could also have a straight line, but most of the curves we're dealing with, we're not going to bother with having actual straight lines in them. They'll be polynomials generally that we're graphing. So these are your four options. And when I look at these, let's actually go ahead. I'm gonna draw. So I'm gonna copy over these four green things, and I'm gonna sort of take a look at what we've got there. So remember, we had that, and that. Those were kind of our four possibilities, if you will, for what we could draw. And I'll be more careful there. These are kind of the four possibilities for what you can draw. And let's actually do this. Let's label these 1, 2, 3, and 4. And all I'm going to do here is I'm just going to point out this curve right here. That right there is number 2. That's me increasing and concave down. This part right here, that's going to be number 4. That's going to be decreasing and concave down. Here, that's going to be number 3. That's going to be decreasing and concave up. And then here, well, really here and here, this whole section is going to be increasing and concave up. And so these are basically just your four options there. And so that's kind of hopefully boils it down to something a little bit simpler that you can think about. You really just have 4 possible curves that you can draw, and then you're just kind of connecting the dots. So for this sort of final just wrap up of everything that we've seen, um, here are steps for sketching a curve, everything all said and done. The first thing is domain. I know in this problem, we had a nice simple polynomial. It was a cubic function. It was nice and simple. We didn't have any issue with domain. But in general, you want to really, really worry about domain. If you have something like an asymptote, or if you have a discontinuity, maybe it's a removable discontinuity, a hole, or maybe, maybe you've got just something funky going on. You got to be careful about it. The next step, and again, we didn't have to do this in ours, we kind of got lucky, but plot the y-intercept. I like to start right, get your y-intercept, and then boom, you've got a point on your graph that you can make sure that your function goes through as you're sketching it. Then plot the x-intercepts, the critical points, and the inflection points, and plot them as ordered pairs. So make sure you're getting both the x and y values for all those. And so obviously, in order to plot these, you have to find them. And that's going to be all that work for f of x equals 0, f prime of x equals 0, or undefined, f double prime. Ooh, careful, careful. I almost got myself here. Concavity change, which might be where f double prime is equal to 0 or undefined. But in general, inflection points are just when the concavity changes. So you have to do all of that info. You have to solve the function equal to 0, the derivative equal to 0, and the second derivative equal to 0 to even find these points that we're talking about. Then just find their y values once you have the x values. Do your number lines, do your test points, find those regions. That's going to give you those shapes of those graphs. So that's going to just tell you whether you need to draw, here, here, here. These aren't in the same order of which I drew before, but that's okay. Those are just your 4 options right there. That's going to tell you those. It's going to tell you where you're positive, where you're negative. And then basically you're just connecting the dots right after that, just going section by section and look at your number lines and figure out where, is my function, my derivative, and my second derivative. Are each of those positive and negative, and in what sort of matchup, and what sort of scenario, and what combination do I have all those? And you just connect the dots in an appropriate way. You should be able to tell fairly quickly what your graph is going to look like. I mean, we've got this graph right here, and really this is one option. I mean, maybe we could have drawn something like this, like that, or I don't know. Maybe it could have gone funky and done something like that. But the thing is, I don't think that doesn't make sense, because I've got critical points all here based on how I incorrectly drew it. I've got all these critical points that we didn't find before. So really, once you have all of your points written down and graphed, it's going to be pretty hard to mess it up at that point, because there's really not that many combinations of what you can do, especially when you take into consideration these sort of you really only have 4 curves that you can draw. And so that's going to be it. I'll go ahead and end it there with just that big last reminder of domain. I can't stress that enough. The really interesting functions have domain restrictions. They have issues if they're with their domain, and we will graph those. So domain, 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 keep that in the back of your mind at all times, and we'll go ahead and call that the lecture.